So in the yesterday's class, we had seen regarding the actuators and valves, as well as LEDs and LCDs, along with the 7-segment LED displays. So in the next topic, we shall see the information regarding the motors, electric motors. So these motors basically convert electrical signal to the rotational output. So these electrical motors provide mechanical movement over a wide range of positions and at variable speeds also. Okay, so you can have the varying speeds, okay, where these motors are able to convert the mechanical movement into the variable speeds. Yeah, so these motors are used in, say, for example, the gears or the screws, so as to convert the linear motion or speed. So figure 1, so as you can see here, so this figure 1 is a natural magnet, what you are seeing in the middle, okay. So we have here a magnet like having north and south pole, and here are the 4 stators, okay, which are stationary. And on these stators, we have the winding of the coil. And for these coils, I can pass the current. Okay. So this magnet will be acting as the rotor, and as well as we have 4 stators. Okay. So like in the figure, you can see a natural magnet where you are seeing in the middle. And the circular thing is a electromagnet. Okay. So when the current flows in this, it behaves as a north pole, right? And opposite end will be behaving as a south pole. Yeah, so we have the north pole and south pole of permanent magnet, and this is attracted towards it. And when the current stops flowing in this, it stops behaving as a magnet. So until the current is made to flow in this, it behaves as a magnet. And when the current stops flowing in this, it will be no more acting as a magnet. So you can also see the series of energizing of these coils. Okay, so we have these coils to be wound on the stators. You can see the series of energizing of these coils. It will make the rotational motion. So by energizing the electromagnet clockwise, the movement will also happen in the clockwise direction. And if the magnet is energized in anti-clockwise, so then the anti-clockwise direction, so we have the rotation. And also, if I'm energizing and de-energizing the magnet in a certain speed, so I can also have the control over the speed factor. Okay, so you do have even something called as stepper motors. So like in case of the stepper motor, so that the movement is happening in terms of steps. Okay, so we can have the control over the steps of the stepper motor. The stepper motor is a simpler of any kinds of motor that we can control with the digital system. So its operation is shown in the simplified figure. So the motor consists of a permanent magnet rotor, and this is mounted on the shaft. So surrounding the rotor is a stator, so where we have a number of coils that can be energized so as to form the electromagnetic poles. Okay. Like in the figure, you can see that the coils are energized in a sequence. Okay, so the motor is attracted to the successive angular positions, stepping around through one rotation. The magnetic attraction holds the rotor in position, and it's also been provided so as to have not much two opposing torque. So from the load connected to the motor shaft. So we also have, apart from the normal DC motor and the stepper motors, so we do have something called a servo motor. So these servo motors will be able to provide the continuous rotation, and the motor itself can be a simple DC motor where we have the applied voltage, and this applied voltage will be determining the motor's speed, and the polarity of the applied voltage will be determining the direction of the motor. So the servo function of the motor involves the use of feedback. So this feedback is basically used to control the position or the speed of the motor. So like if you are willing to have the controlling the position, so we can attach a position sensor to the motor shaft. So for controlling the position, so we can make use of a position sensor, right? So the position sensor can be used to the motor shaft. So we then use a servo controller circuit that compares the actual and the desired positions. Okay. So along with the position sensor, so as to have the control over the position, so we can also make use of servo controller circuit that compares the actual and the desired positions. That will give us a driving voltage for the motor that depends on the difference between the positions. So like if you're interested to control the speed, so we can attach tachometer. So this tachometer is nothing but a speed sensor. So this tachometer can be attached to the shaft, and you can use a comparator so as to compare the actual and the desired speed, okay, to yield the motor drive voltage. Okay. So like in both the cases, so whether we are interested in controlling the position or we are aiming to control the speed, so in both the cases, we can implement the servo controller as a digital circuit, or we can also use any embedded processor. So we need to have the use of a digital to analog converter so as to generate the drive voltage for the motor. Yeah. So we can make use of these figures. So after this, you have the DAC controllers. Okay. So this DAC stands for a digital to analog converter. So like with respect to the embedded controller, so these embedded circuits, embedded controllers, so gives the output in terms of digital form. So but for our actuators or solenoids, so these devices will be in need of analog input. Therefore, so we need to have the conversion of the embedded processor's digital signal in terms of analog output. So to have the control of the transducers or equipment as such. So you can find here, so basically two types of tags. Okay, so you can basically find two kinds of digital analog converters. So one is R string DAC. Okay, so here we are seeing the R string DAC. So we have a string of registers. As you can see here, 1, 2, 3, 4, 5, 6, 7, 8 number of registers are used. So we have here 8 number of registers. Because I need to have the conversion of the input from 0, 0, 0 to 1, 1, 1. So from 0 to 7, in terms of binary, it is 0, 0, 0 to 1, 1, 1. So for that reason, I need to have 8 levels from 0, 0, 0 to 1, 1, 1. Okay. And if I make all the inputs A of 0, A of 1, A of 2 as 1, 1, 1. Okay. So we have the activation of the switches as shown by this line. Okay, so basically we have here, so this reference voltage gets applied here, and we have this as a series of resistors. And basically, we can use 8 number of resistors, and at the voltage tappings of each and every resistor, I can make use of some switches. Okay, so we have these as the input lines A of 0, A of 1, A of 2, and as we have here 3 number of input lines, I can have 8 combinations from 0, 0, 0 to 1, 1, 1. So suppose if the input is 1, 1, 1, suppose if the digital input applied to the DAC is 1, 1, 1, in that case, the upper switch is as shown here, like this switch, and this switch will be activated. Okay, and the lower switch will be in the deactivated position or in the open circuit position, and the upper switches, this one, and this switch will be activated, where A of 0, A of 1, A of 2 being high. So then this switch, and this switch will be activated. Why? Because as you can see here, so this line is intended for A of 0 equal to 1, and this line is intended for if A of 0 is equal to 1 means obviously here I'll be having the A of 0 bar. Okay, So hence, if EF0, EF1, and EF2 are high, high means the upper switches which are connected to this line, this line, this line, and this line. So called this switch, and this switch will be activated, and I can have the flow of current via these switches, and so as to have the analog output corresponding to the digital input 111. And if you see, suppose if this EF1 is equal to 0. So for 101 of digital input, where EF2 is equal to 1 and EF1 is equal to 0 and EF0 equal to 1, means EF0 is equal to 1, right? Hence, this switch will be closed. And as the EF1 is equal to 0, okay, right? Like in that case, this switch will be activated, okay? And for EF2 is equal to 1, okay, and this switch will be activated, right? So hence we have the conduction path from this switch, and via this particular switch. Why? Because here now EF2 is equal to 1, okay. So for high output, so for higher value of input, suppose if any input line is high, means the upper switch will be activated, and for any input line being low, the lower switch will be activated. So here, like in this case, as EF2 is equal to 1 means this switch will be activated. Hence, this switch, and this. So we have a conduction path here that will leading to the output B out. Okay. Again, if you look at the third combination where EF0 and EF1 and EF2 are 0, 0, 0 means now we can see the lower switch to be activated. Hence, the conduction path is also shown here. Okay. So the topmost switch and the bottommost switches and the connections are being shown here. And according to the given input, suppose if all the input lines are 111 means the top switches will be activated. And if any input line is being 0 means the lower switches will be activated, thereby establishing a conduction path. And for the three combinations of input, the input being 111, or input being 101, or input being 000. So for these value of input, the conduction path is as shown in the line. Okay. So one more kind of the DAC architecture is R2R ladder DAC. Okay. So you can see the connections here. Like in the above figure is for the 4 bits. Okay. So this figure is corresponding to the 4-bit R2R ladder DAC. So if EF0 and EF1, EF2, EF3, EF0, EF1, EF2, and EF3 are all ones. Okay. So 1 means it will be connected to the upper connection. Okay. And if all these EF0, EF1, EF2, and EF3 are 0 means like these will be connected to the ground connection. Okay. So if EF0, EF1, EF2, and EF3 are all ones, so then for all these 2R registers, so you can have the flow of current. Okay. So from the VF. Okay. So the voltage drop across the complete R2R ladder is coming into picture, and this is applied to the inverting terminal here. Here is the inverting terminal of this op-amp. Okay. So if all EF0, EF1, EF2, EF3 are all 111, so then for all these, the 2R register will be having the flow of current obtained from this reference voltage VF. So the voltage drop across the complete R to R ladder is there here, and that gets applied to the inverting terminal of this op-amp. Okay. And of course, like as it is the inverting operation amplifier means obviously the output will be inverted. So now if input is say 1001, where A0 is equal to 1 and A3 is equal to 1, and A1 of 1 and A2 are 00. Okay. In that case, suppose if input is 1001, so then In this case, the voltage in the second and the third branch. Okay, so you can say this second and third branch will be open circuit. So now we see that only the top and the bottom branches are being shorted. Why? Because the input for A of 0 and A of 3 are equal to 1, 1. Hence, so we have a shorting of the like the first and the last branch, and we have open circuit in AF1 and AF2. Okay, so the middle rows are open circuited, and the bottom and top rows are short circuited. Okay, like this is how the voltage level will be changing. So if all these inputs AF0, AF1, AF2, AF3 are 1, 1, 1, 1, like okay, so if all the input lines are 1, 1, 1, 1, you can get more voltage drop at the inverting terminal, and output will be obviously high. Okay, so you can have this figure to be explained from the examination point of view. So next we have the keypad controllers. Okay, so we can have a keypad like earlier in the previous slide while we started this interfacing IO interfacing model 4. So like we have seen a keyboard, okay, and for this we have a controller also, and this is a dedicated to this particular keyboard. Okay, so we do have something called as IO controller, and it is so much more complex when compared to a simple keypad controller. So in this module 4, like we've seen the construction and operation of a 4x4, or to have any size keypad. Okay, so like so as to have the operation of a keypad, so we have a separate controller meant for it. Okay, that we call it as a keypad controller. So like here you can have even the IO controller as well. Okay, so these IO controllers are much more complex when compared to the keypad controllers. So the simplest form of a control consists just of an input register. So we have the input register that is able to capture the data from the input device, or so you can have the use of output register so as to provide the data to the device. Okay, so this usually like usually we have several input and output registers. So we need to select so which register to read from, or which register that we have to write. So, and we also know that each register will be having its own address. Okay, so when the embedded processor needs to access the input or output register, so the embedded processor will be able to provide the address of the required register, and we can decode the address to select the register, and only enabling the reading and the writing of that register. Okay. Uh, so we can use this address decoding circuits. So these address circuiting circuit connected to the processor so as to identify so whether memory or IO registers are being accessed, and we can enable the memory chips or appropriate register as we require. Okay, so here we are seeing the keypad controller, and this is a simple keypad controller. So we have dedicated controllers for one device only. Say if greater than one device is being controlled by controller, and it is not a simple controller in that case. Okay, so like it is a more complex IO controller which are also available. So but here we are dealing with the keypad control basically. So this is a 8-bit processor. Uh, yeah. So what I'm showing here is called the government processor, and here we have a keypad controller. So now let us discuss with this government processor. So what basically is this government processor? So like this is a complete processor actually. So this processor will be interfaced with the many processors. So but in here like it is shown to be interface with the keypad controller. Okay, and again this keypad controller is having a keypad here. Okay, so this keypad is being interfaced with the keypad controller, and in turn this keypad controller is connected to the government processor. So this government processor is basically a 8-bit processor core, and that is intended for the education purpose, and it is similar to a 8-bit microcontroller, uh, like which is meant for small embedded applications. So, but it has an instruction set architecture more similar to a RISC processor. Okay. So basically, this gumnet processor is a complete processor, and this processor will be interfacing with many processors. So, but in here, so what we're showing is to be interface with a simple keypad controller. Okay, so for this keypad, so we have a keypad controller, and for this keypad controller, this gets interfaced with the gumnet processor. Okay, so you can see the connection between the keypad with the keypad controller here, and with the keypad controller with the gumnet processor. So you can see that sorry, so you can see that the signal coming from the keypad, here it is. So the signal coming from the keypad to the keypad controller is fed back to the gumnet processor. Repeat, you observe here the signal that is coming from the keypad and to the keypad controller is fed back to the gumnet processor, because finally at the processing that will be done in the gumnet processor only. And we have the use of the feedback to be made here. You can also see the port data output here. Please. So port data output of command processor is being connected to data input, data I of the keypad controller. Similarly, the port cycle 0, here it is. So port cycle 0 or the output cycle port of the government processor is being connected to the input cycle. Okay, CYC underscore I is the input cycle of the keyboard of the keypad controller, and CYC underscore 0 is the output cycle port of the government processor. And also you can see the connection of support write enable, here it is. Support write enable. Okay, so when it receive when it is enabled, okay, so when we have the activation of this port write enable, so when it is enabled, it is write underscore I at the keypad controller. Okay, and so you can also see the strobe signal. So this strobe enable, okay, so this strobe enable will be able to enable the keypad controller. Okay, so therefore, to activate this strobe enable, two things are very much important. That the port address output is given, and this address must be equal to the keypad port address. Here it is. Okay. Yeah. So you can find here greater than one number of ports. So for interfacing in the government processor, therefore, so both input to the AND gate, what you are seeing here. So the both input to the AND gate are equal. So then this keypad controller will be activated. So why? Because that we know the basic property of AND gate. So when all the inputs to the AND gate are high, means then only the output will be high. Okay. So here you can find greater than one port for interfacing in the government processor. Therefore, if and only if both the inputs of this AND gate are equal, then only the keypad controller will be activated. And you can also see the status register. So these status registers will be containing the bits. Okay, so these bits are responsible to reflect the status of the device, and it is read by the processor. Okay, in the diagram, so the status registers was acknowledgement high, right? So this acknowledgement high that is going back to the government processor. It indicates that like here it is. Okay, so the status register was acknowledgement high, that is going back to the government processor. It indicates that the status is, it indicates that the status that is working. Suppose if it is 0, so then it indicates that it is not working. So basically, so this acknowledgement signal is high, means that the processor is working, and if it is equal to 0, that indicates that it is not working. And it is always be in the real mode. What we need is so both the control and status registers for IO controller here. So by seeing the keypad controller here, we need so both this keypad controller and government processor to be activated, and so as to have the communication between the keypad controller and the government processor. So next one is the ADC controller. The earlier, like we have seen the successive approximation ADC, right? And we have seen these many ingredients inside a successive approximation ADC, which we like what we have seen here, that we had used so one analog input sample and hold circuit, and we had used four number of analog reference voltage, and we had also used a control register, and we had the use of status register and input data register. Like earlier, like we have seen operation of the flash ADC as well as the successive approximation ADC. So, but here we need to have the study of ADC controller as well. Like in place of the keypad controller, like in the previous figure, where we had the use of a keypad controller. Okay, so we have now the ADC controller. Like in place of the keypad, that we have ADC coming into picture. So how a government processor will be connected through a ADC controller? So like we have seen a successive approximation ADC, like where we had used so one analog input with the sample and load circuit and all these ingredients. Okay, yeah. So now we'll see the diagram of the ADC controller. So you can see that so we have here many connections. So you can see like what all things are there in the ADC. All will be coming into the diagram of this ADC. Here it is. Okay. So whatever the blocks, what we can find in the ADC, all will come into this block diagram of ADC. Like on the right hand side here. Okay. We can also see here this input voltage. So this analog input voltage is applied via the sample and hold circuit to this ADC. Here it is, like this line of what I'm showing, and this is representing a sample and hold circuit. So for which the input voltage V is applied. Okay. And you can also see this reference voltage. Okay, so this VF0, VF underscore 1, 2, 3 as a reference voltage that gets applied to these switches. Okay. So start is also there here. Okay, so we have a start signal here. Start is here. So the clock is there, and reset is added. Okay, so reset is also added here, and done is high, and V naught is given. Okay, I mean V out is given. Right. So you can see that so your V in can directly come from the input point V in. So, but if ADC is busy in, suppose if ADC is already busy in converting or in conversion other data, so the next data may be sampled and already held in the sample and hold circuit here. Okay, so that is sample and hold circuit will charge a capacitor, here and hold the value of B in for some amount of time. So this sample and hold operation is controlled by this Q2. Yeah, there it is. Okay, so we have a connection of Q2 to sample and hold circuit. Okay, right, and this Q2 is also be connected to the start and done lines. Okay, so this sample and hold operation is controlled by this Q2. Okay, the Q2 control signal, that is Q2 is a control signal to start. It is Q2 will tell so whether to start or not, and Q2 will always tell so whether this Vn is to be held or not. So if this Vn that is Vf, so this Vf is your reference voltage, and a decoder of 2 cross 4. So you can see here 2 cross 4 decoder is also used here. Say if D0 and D1 are equal to 0, 0. So then this Y0 will be switched and output will be 1, 0, 0, 0 we get. So this will make one level of reference voltage. Okay. Again for 0, 1 combination of D0 and D1. So Y1 will be selected and this particular switch will be selected where we have the reference voltage as Vf underscore 1. Similarly for 1, 0, so Y2 line will be selected and this particular switch will be activated where we are selecting the second reference voltage Vf underscore 2. And similarly for 1, 1 combination of D0 and D1, so Y3 will be selected and this particular switch will be closed and we have a connection of VF underscore 3. Okay. Yeah. Explain all these things. So this Q0 and Q1 are the 2 bits. Okay. So this Q0 and Q1, right, are the 2 bits that are making Y0 to Y3, controlling it to give you the different levels of the reference voltage, VF0, VF1, VF2, and VF3. Okay. Yeah. So there. So these VF0 and VF3 will go into the ADC, as you can see here. So this reference voltage VF0, VF1, VF2, VF3, that will be applied to this ADC. Okay, that will be going into the ADC, and this is governed using only 2 bits Q of 0 and Q of 1. Okay, so this 2:4 decoder is basically used to take care of this reference voltage VF0 to VF3. Yeah, so can add this information for this ADC controller. Yeah, so now in the next class, let me go for the next topic. So until that, you can keep revising the things. Like in this particular class, let me discuss something regarding the DC motor, okay, as well as stepper motor and servo motors, as well as the 2 kinds of DACs, right? R string DAC and R2R ladder DAC, along with the keypad controller and ADC controller. Okay. Thank you.